Guys, allow me to introduce this fellow. I've known Johnny since 1998. And he's been professor of electrical engineering at UT Arlington for 35 years now. And he really understands propagation and antennas. And Rodney, he's still puzzled by yours. I just wanted to introduce him because he's a good friend of mine, and I appreciate him coming out here. And I could be wrong on this, but I really think he knows what he's talking about. So, Dr. Bredow, table's yours.
Yeah, just to give a little bit of my background, I'm currently working on RF type problems, but they're more related to like drone communications, or I was talking to Bud about near field antenna measurements when you're characterizing antennas. An interesting problem that currently looking at with some mechanical engineers is they're looking at data servers cooling, but now they're looking at possibly immersing the whole server in a liquid of some sort, as they want to understand how that's going to affect the high-speed buses and so forth. So those are some of the interesting problems I'm working on. And so I'm giving kind of a broad brush to this whole subject of propagation. Some of it relates probably more to like cellular communications, but I hope you find it interesting and insightful as well. And, I hear a lot of neat things coming from this group too, from what Bud's talking about. So let's see. Oh, there we go. Okay. Oops. All right. So this is kind of a starting point for when we talk about propagation in some of our classes. So I don't know if you have seen this kind of thing before, but it's just called Friss equation. So when people talk about communications, like space communications or whatever, this is kind of the starting point they use. And so the gain of the antennas are the G's, as you can tell, and the range between the two antennas is just R, and PT is the power input to the transmitting antenna, and PR is the power delivered to the input of the receiver. And so, of course, this is pretty much for free space communication. Okay, so it applies well to communicating with spacecraft, for example, or when you're in space. But it has some limitations to terrestrial communications, and so that's what I want to talk just a little bit about. And so just to introduce you, some of you may be familiar with the concept of using rays to represent propagating waves. And so if you have a situation like the one on the left where they're pointing outward, that implies spherical waves being propagated. And so usually we think of that being from the source outward. But when you get far away from that source, the waves become approximately planar wavefronts. And that's kind of when we talk about how waves interact with the environment, we're usually talking in terms of plane waves. And so you just see a single vector that's implying a plane wave. Okay, so some of the basic interaction phenomena that we talk about, and these terms I'm sure you've heard one place or another and pretty familiar with them. Some of you, reflection, refraction, diffraction, absorption, scattering, it all sounds pretty simple, but when you get into the nuts and bolts, there's some complications. And so that's one of the things I wanted to talk just a little bit about. So we introduced the idea of boundary conditions. And so a boundary condition is kind of like when your transmission line is connected to the input of your antenna, there's an impedance input to your antenna, there's an impedance in your transmission line. And so if there's a mismatch, you get a reflection, right? And so it's kind of the same in terms of wave propagation. When you interact with a medium that has different electrical properties than what the wave is propagating from into, then there's a reflection that occurs. And so the impedance matching problem that you're used to with circuits, we show as a propagating and reflected wave. So V0 plus is the propagating wave toward the load. V0 minus is the wave propagating back from the load. And so eventually you end up with the equation gamma, which I think you're probably pretty familiar with, where you're just looking at the reflection coefficient where you have an impedance, potentially impedance mismatch. So, but when we talk about wave propagation, we have additional degrees of freedom, I guess you could say, because now we can control the angle relative to a surface of some medium. And so the reflection coefficient, the transmission coefficient, and so forth will vary depending on the polarization of the wave as well as the angle of incidence. So we define angle of incidence as relative to the normal of the surface. And so the idea of specular reflection, I think you're familiar with, where you have the angle of reflection is equal to the angle of incidence. And then depending on the particular medium, oftentimes we're going to have a wave that's transmitted into the medium as well. So that's the wave that is typically refracted in some capacity or another. Now, the diagram on the right just gives a little bit more insight into what's happening, because at a boundary, we're looking at things like what's the tangential electric field, what's the electric field component that's normal to the surface, and the same thing with the magnetic field. And so we know what those boundary conditions are or need to be. And so from that, then we can look at, as a wave goes from what we call a medium with lower index of refraction to one with higher index of refraction, the wave bends, right? So you're shining a light into like water and it bends down, right? And so what the diagram is showing, the different lines represent different phases of the wave as it's propagating. And so as the wave is propagating, the component going down into the surface has to be maintained phase-wise with the wave propagating above the surface. And so that phase matching is then what creates the wave that bends going into the lower medium, because we know that in the medium below, the wavelength is shorter than it is in free space. Okay, and so that's what this is. In order for the impedances to be matched, it forces this wave to bend in this kind of fashion. Okay, there's some interesting things that happen here that sometimes you'll hear about. There's one called Brewster angle. So for a wave that's incident, that's vertically polarized onto that planar interface at just the right incident angle, there's no reflection. Wave does not reflect, it only transmits. And this is an important property that's used in like Polaroid lenses, for example, sunglasses, anti-glare type devices. And so it can also convert, let's say, a circularly polarized wave into a linearly polarized wave, because it's, especially if you're counting on the reflected part, it will reflect only the in the case of the Brewster angle, it will only reflect the horizontally polarized component. There's another thing that's even more interesting called critical angle. And so this is where you have all internal reflection. So I don't know if you've tried this experiment, but if you haven't, get in a pool with a flashlight. The pool flashlight's made for pools, right? And shine the light underneath, right? And you'll see that at some point the light will all be reflected. It's kind of a fun little experiment to do. But another interesting thing that happens is if the wave exceeds the critical angle, there's this additional component that forms on top called an evanescent wave. And that's caused in order to force the boundary conditions in terms of the tangential electric field component that I described earlier. But that wave decays as you move away from the boundary, but it's not propagating. It's just like a field that exists outside that medium, just as in response to the component that's internally reflected. So it has some different applications that we won't get into here, but it's kind of an interesting one. So when you think of this whole business of the reflection and refraction and so forth that I just described, how do you apply that to practical scenarios? So you can say, yeah, if I look at a wall, I can say, okay, that's pretty flat, so I kind of know what the reflection is going to look like off of that. But if I'm talking about the surface of the Earth somewhere, I know that's not flat, really, right? At least not optically. And so how do I define roughness criterion in order to say, okay, well, it's a good approximation to use this Snell's law of reflection or refraction for a particular scenario? And so in this particular case, we look at these different rays that are coming from a particular surface associated with the wave, and we say, okay, well, as long as they're only less than pi/2 radians out of phase, no more than 90 degrees out of phase, then we're going to say, okay, well, that's smooth enough. We can apply this idea of the Snell's law. There's also an area criterion, because as you make this planar surface over which reflection occurs small enough, the wave no longer becomes this specular thing, but it starts looking more like a pattern, it's diffusing or diffracting outward, like an antenna pattern in a sense. But if you want to be able to apply this idea of specular reflection, then we need to specify what does the area need to be for that wave to be treated as a kind of specular reflector. And so this is where the idea of Fresnel zone comes into play. So in this particular case, again, we're looking for situations where, as we look over that surface, we want to make sure that all the ray components are less than λ/2 different from each other in order to be able to apply that concept of Fresnel zone. If you have any questions or say, what in the world are you talking about, or how does that apply to what we're doing here, feel free to ask, okay? So I'm just giving you a broad brush on things, and I'll kind of leave it up to you to figure out how you want to try to apply it. Okay, this idea of Fresnel zones also applies to if you're trying to do a line of sight transmission. And so nowadays we don't see so many microwave links, point-to-point microwave links, because of all the internet, fiber optics, and spacecraft communication. But one of the planning aspects of these types of systems involves in what are the obstacles in between the two antennas. And so how likely is the wave to interact significantly with those obstacles? And so again, we define that in terms of this concept of Fresnel zones. And so we want to make sure that at least 80% of what we call the first Fresnel zone, there are additional Fresnel zones outside of that apply to different phase shifts, but make sure that at least 80% of that first Fresnel zone is unobstructed. And so I don't know how many of you like lighthouses. You've probably seen Fresnel lenses and all that sort of thing based on the same principle, right? And so that's an important consideration.
Quick question.
Yeah. Yeah.
What determines the height of that Fresnel zone?
Okay, so the Fresnel zone is, you see the center of it is kind of the line of sight between antenna A and B, and then it goes outward from that. It's kind of circular.
What determines how the diameter of it?
Yeah, the same criterion that we had back here. So here the Fresnel zones in reflection become elliptical once you project them onto the ground. But we're still looking at that same, looking at the different rays that are propagating from one end antenna to another and making sure they're no more than λ/2 different from each other. And so that's kind of what we're looking at is within that, oops, I went backwards. Within that Fresnel zone, that first Fresnel zone, the circle, all the different rays are within that λ/2 of each other.
If you double the frequency of your signal, does the zone get taller or shorter?
So if you double the frequency, the zone should get shorter, right? Because your wavelengths are getting shorter. And so, but this is important in these types of systems, as I'll talk in a few minutes, the idea of weather-dependent ray refraction that occurs in the troposphere. So the waves aren't necessarily propagating in straight lines. They're actually bent by the atmosphere, troposphere in particular, because the refractive index is changing. It just depends on the different conditions. Things like water vapor, partial pressure, the atmospheric pressure, temperature, those all play into what the refractive index of the air is. And so as that varies as a function of height, you can see that there's going to be a refractive index variation. And so it depends on how that is as to which way the wave is going to bend. And so if we have a situation where the wave is influenced to bend downward, you can see that that could, put an additional restriction on how high you need to be above the obstacles. Okay. Another interesting thing about waves is they don't really propagate in straight lines. You know that, right? And so, but this is a neat way to kind of describe that, what's happening here. So this thing called Huygens principle, and so it's worth looking up. It's kind of an intuitive concept, is that each point along the wave, in the part A, I'm showing a plane wave that's propagating, but I'm showing that each little point along that wave can be treated its own little wave generator, in a sense, propagating outward spherically. And so you can see a number of different sources. And clearly on the right-hand side, part B, as we're propagating out spherically, the same kind of thing is happening. But what happens as a result of, especially toward the edge of the wave, you can see that the tendency is going to be for the wave to start diffracting, bending outward, right? And so that's exactly what happens. And so in the case of like an antenna, the wave is propagating out, has a certain characteristic up close to the antenna. As it's propagating away, this kind of constructive and destructive interference with these different wavelets is occurring. And so we're wanting to see what's the distance, how far do I need to go before I see an antenna pattern that's going to stay the same. It's not going to change the pattern itself. Clearly, the energy will decay, right, as we propagate outward, but the pattern will stay pretty much the same. And so that's where we have different field regions associated with antenna radiation. And so, so the bending away is described as considered to be diffraction. So when you hear people talking about these same kind of wave phenomena, but from an optical perspective, that's what they'll talk about. They'll talk about a diffraction pattern. But the diffraction pattern is pretty much the same thing as an antenna pattern at radio frequencies. Okay, so how fast does the wave diffract? How fast does it bend out? And as I indicated, it depends on the wave that's propagating, how many wavelengths are there across that wave. And so in the case of the larger the number of wavelengths across that wave, kind of the slower it diffracts as you move outward. And so I use the example here of a laser pointer. If you take a laser pointer, you can point it quite a ways and it's still a spot, right? You have to get quite some distance away before you can actually see a pattern associated with that. So, I don't know, probably in some science class or something, you did this slit diffraction experiment, maybe, or you take a slide of glass, coat it with paint, take like a razor blade, and shine a light through it, and you can actually see the diffraction pattern, because now you've restricted how many wavelengths are across that particular light beam. So at any rate, the criterion that we normally use to describe how far away you need to be from an antenna before you can say, okay, the pattern is pretty fully formed, is given here by this equation. This is not hard and fast. It's more of a rule of thumb. If you need a well-defined pattern, for example, in terms of the depths of the nulls in your pattern, then you may need to go farther out. Okay, but this is for most practical applications. This works pretty well. So the D has to do with, in general, we just say that's the largest dimension of the antenna. So clearly, if it's a wire antenna, they're just one dimension right now. But in terms of like an aperture antenna of some sort, this is just the maximum dimension of that antenna. Okay. Interestingly, this idea of diffraction, notice there are obstacles such as a knife edge. If you place a knife edge in this propagating wave, it's going to enhance that diffraction effect. Because now you've kind of defined an edge for that beam, and now the wave's going to diffract down into we'd consider to be a shadow zone, for example, if we were thinking it was a straight line propagation. Right? At any rate, that's a well-known phenomenon, and this curve here on the left kind of it's not too readable up there, but it tells you how fast diffraction occurs according to this parameter V, which is defined over here. So you can see that as the wavelength decreases, gets smaller, you get shorter wavelength, the diffraction, this V parameter, increases more quickly. So that's telling you that as you get to shorter and shorter wavelengths, the efficiency of that diffraction provides a communication to something that's in the shadow region is not as good at higher frequencies, lower wavelengths, than it is at the lower frequencies, longer wavelengths. So, of course, in cellular communication, we rely on things like reflection and this kind of diffraction to supply a link to us from the cell tower, right? Oftentimes, especially you get into a more rural area. And so these are important phenomena to understand. Now, in the case of something that's a more gradual edge, like a rounded hill or so, the diffraction isn't as effective. Okay. Questions up to this point?
Very similar to sonar.
I'm sorry?
It's very similar to sonar.
Yeah. Sonar is, again, a wavelength. Just have a little bit different kind of wave instead of being EH, right? It's pressure and shear kind of thing.
Now, you were talking about the diffraction being less effective. I would think that diffraction is something that I'm not wanting to use. Are you saying that diffraction is a good thing in this case?
Well, I'm saying refraction is something we kind of rely on in some cases. You're out in a rural area on your mobile device, and you may be some distance away from the tower, so that in that case, the diffraction may be helping you to have a link.
All right. Yeah. It's not something that you're designing in the system, though.
Not typically,
Okay.
right. But diffraction can play a role in when you're designing an antenna as well. Once you've got like a ground plane around your antenna, those edges actually contribute to diffraction. So it may give you a back lobe that you don't want in the case of an aperture antenna. Yeah.
They talk about a piece of glass and laser. Right? Yeah, touch this. Shine. That's like you can see interference patterns through the two slits, right? And anyway, that's
Yeah, you can see the patterns forming and the effects of them. In fact, one of the interesting applications of something like that is, using a micrometer, if you if you're measuring thickness of something, that only works down to a certain point, right? You're dealing with something that's like 10 microns in diameter, strand of hair or whatever, you're not going to do that with a micrometer very well, right? But if you put a piece of hair as an obstacle, see what the diffraction pattern looks like, then you can use the spacings there to infer what the diameter of that piece of hair is. So that's a different way of measuring thickness where mechanical approach is not viable. So anyway, but those are good to relate to those kind of experiments. Okay, so I was going to move on and talk about the subject of ground waves. Anybody use ground waves for communication? Okay. Especially if you're down in the hundreds of kilohertz or tens of kilohertz and maybe up into megahertz or two, ground waves can be helpful. Right? And so what is it that's happening with the ground waves? So there are different kinds of ground waves or surface waves that are talked about, and I won't try to get into that too much. So that's why I put the term xenic up here, because it applies more to the phenomena that's occurring here when we're trying to use ground waves in communication. Okay. And so I just put a couple of points as to what's happening here. And so I'm not big on reading off slides, but in this case, so the wave is launched, it's propagating outward, it's diffracting down toward the surface of the Earth. A portion of the wave then is starting to interact with the surface, right? And so how does the surface then help sustain the wave so that it propagates further? You know, and so that's something we can talk about here shortly. But if it interacts properly or effectively with the ground, then the ground can actually help extend the range of communication, right? And so I indicate where it's, and you can find all this information. But at any rate, for very low frequencies, even into lower, middle, and medium frequencies, when the wave is vertically polarized, it's not nearly as effective if the wave is horizontally polarized. And that has to do with when you've got a vertical polarization with the electric field extending down vertically into the ground, it's inducing charges to move around within the ground. Okay, and those charges are essentially reinforcing that wave. And so keeping it going as it's propagating outward, as well as the ground is kind of confining the wave so it's not spreading as quickly. So you're sort of sustaining the energy farther out. Now with the horizontal polarization, if you think of the example of a ground plane, and as you bring an electric field close to a ground plane, you're inducing an electric field in the opposite direction. So you're actually forcing it down to zero at the ground surface.
That one last sentence again, say it one more time.
Okay, so
Forcing it down.
yeah, let's say that you've got a horizontally polarized wave, and so as it's interacting with the surface, in the case of like a good conductor, the electric field that's present will induce an electric field in the opposite direction in the surface, on the surface of that conductor. And so that will effectively cancel the electric field and forces it kind of away from the surface. And so that happens to some extent with real substances, not just perfect conductors. But again, that's effective mostly at these lower frequencies. And the higher conductivity of the soil enhances the ground effect for vertical polarization. So that's kind of interesting. But at higher frequencies, this isn't effective. Charge movement within the soil is less efficient in sustaining the wave as you go to higher and higher frequencies. There's more loss involved.
What does it do over water?
So over water, yeah, at these very low frequencies, it actually sustains it pretty well. When you get down into the 10 kilohertz range, for example, that has been used for subsurface communication. But it's obviously because it's such a low frequency, you can't send a very high data rate though through it. But yeah, that's interesting. As you go down into that frequency range, you can actually propagate into water, right, seawater. But as you get to higher and higher frequencies, the electromagnetic waves are largely absorbed by water, right? As you move to higher frequencies.
Hey, John, question.
Yeah. Yep.
Someone on Zoom has a question. David Edelman?
No, he doesn't. That's his mouse.
Oh, okay, never mind.
I like Jacob there too. Yeah.
So John, if I'm understanding what you just said, at the lower frequencies, ground waves exist only because of this relationship with the vertical antenna, vertically polarized signal wave, and conduction in the ground.
Right.
So basically that means that there is no ground wave if I'm horizontally polarized.
It's pretty weak, right? The horizontal polarization because of that effect.
So at what frequencies, if I'm vertically polarized, at about what frequency does ground wave go away? It doesn't exist.
So I mean, it depends on on how you defined it, but most people say it's in the like 1 megahertz range or maybe a little higher. But once you get down into the low, let's say AM radio band or something like that, it can be pretty effective. And obviously clear down below that, low frequencies, very low frequencies.
And the distance it travel is going to depend a lot on the conductivity of the ground.
That makes a big difference. I do have a plot here coming up, I think that's, in a minute. Okay, so anyway, this is just kind of the illustrating. I try to make sure I include references to all the figures I use because, I don't try to go back and do all this artwork if somebody else has already done it. But, if I was selling this, that'd be a different story, right? I'd have to pay them something. But it's called free use, right? Or fair use, I guess.
Academic fair use.
Fair use, yeah. There you go. So anyway, this kind of illustrates the behavior in a kind of a color graph. You can see it kind of diminishing in strength as you move farther and farther out. Now this one is there a way to zoom in on this or maybe not? I don't know. So anyway, this kind of illustrates the effect. I wish I'd have, it's okay if we can't. So I think this is like a 1 kilowatt transmitter. I'm not sure what the antenna gain is here, but it's telling us what the field strength is here. One's on dB microvolts, the other's on, what's the other scale on the right side? I don't recall. But anyway, what you can see is as the conductivity is increasing, there you go, thank you. Okay, so this is microvolts per meter, and you can see the distance. You can see how fast it's falling off for the different conductivities. So you can see the one we're dealing with, even though epsilon, relative epsilon 70s, the conductivity is now 5 Siemens per meter, and you can see it's really continuing to support that signal instead of dropping off. So, but you get to the very dry ground, which is the leftmost curve, you can see it's dropping off much more quickly. This is 800 kilohertz, by the way.
Now, the minute ago, I think you said in one sentence, we want to replay that one more time. You actually explained why the electromagnetic fields, how they interact in a vertically polarized antenna. That's why. When I read about more, the only decent antenna below, it's like 475 kilohertz. It's got to be a vertical.
Right.
Right? You're about to tell me that. Say something about the electromagnetic.
Yeah, so, think about, a charge or a region of charges. You're familiar with the concept of Coulomb's law, I guess, right? Where what electric fields emanate from that charge, right? And so in the same kind of fashion, when you have an electric field that's produced, in the case of the electromagnetic wave, it's actually attracting charges in a particular region. Okay, and of course it's going to vary depending on what part of the wave you're in, but that particular charge that is induced is going to reinforce the wave, try to sustain it.
Okay.
As opposed to the horizontal case where they're actually, the induced one is actually the opposite direction of the one of the wave that's inducing it. And so that's what's causing the wave to kind of bend away in a sense from the surface.
Yeah, I was trying to get the model in my head.
Yeah.
Okay.
So anyways, it's an interesting phenomenon. Okay. So anyway, I did put references in there. And if you want to look into it further. So anyway, the whole thing of ground waves is pretty interesting, I think. Not that many people make use of it, but there are some that try to work at those very low frequencies. Yeah.
Yeah, so on receiving antennas, I understand, I'm not sure if this is the same concept that applies to like coverage antennas, but they take advantage of the fact that there's a propagation through the wire that's slightly above the ground versus the waves that are traveling through the ground. Although it's only really useful on lower frequencies like below, and typically like 7 megahertz or below.
Mhm.
Is this the same?
Yeah,
Same
it
principle
follows
applied.
in terms of the phenomena that I was describing. Yeah, it's kind of the same thing. As the wave is propagating out, it's also inducing charge and currents in the surface that kind of reinforce what's going on in the wire. Okay, and so there's this broad body of stuff called scattering, and this applies to so many different things. So in general, as I've indicated here, unlike reflection, where we think of like a specular thing happening on a particular surface, scattering is kind of what it says. It's as the wave is interacting with this particular object, it's directing energy in various directions. It depends on what that is as to how that's happening. But anyway, that's the idea of scattering. It's a little bit kind of like, it may not be incoherent, but it's kind of random in a sense. And so a lot of different things we think of it as doing this. And so I indicated some examples, rough surfaces. And of course, that depends on your wavelength, right, as to what the roughness of the surface is. So that's one of the challenges we have in our thinking is when we think about something that's rough, is it's relative to what? Here we have to think in terms of wavelengths, right? So something that looks rough to our eyes may not be electromagnetically rough, right? It's a longer wavelength. And so the same kind of thing here is vegetation, forest canopies, and so on. And typically for these scattering types of things, this isn't universally true, but individual components of like a tree or something like that, if you look at the leaves, how they're scattering, or the small branches and then the main branches and the trunk and all that sort of thing. Typically they scatter if the object is on an order of 0.1 lambda or greater. And of course you've got roughness like on the trunk, right? That's, as you go higher in frequency, it's further scattering energy. And so, I'm sorry?
Give me a zoom in on that chart for you.
If you wouldn't mind, yeah, that might be good. This is just an example of a forest. Yeah, thank you. So this is just an example of a forest canopy. This is at 200 megahertz, and you can see it goes up to a distance of 5 kilometers. In this particular case, the transmitter was set so it was, the main part of the wave was propagating through the canopy. And so it didn't really say anything about polarization, I don't think here. But at any rate, you kind of get an idea or feeling of what the scattering might be able to do. Even at 200 megahertz, you can see over this 5 kilometer depth that I believe the path loss in dB, I believe this is in addition to the normal path loss that you have. And so at any rate, it can be pretty significant, just depending on what frequency you're operating at, what the size of these different components is, and so forth. And so this was the type of thing I was working on my first 15 years, probably at UTA. We were actually, we have a society within, anybody IEEE member in here? Long time ago, okay. So IEEE is a professional organization for electrical engineers, and it has all kinds of societies, and one of those is called Geoscience Remote Sensing. And so I was pretty active in that one for quite a few years and still off and on. And we actually held a conference here in Fort Worth back in 2017 down at the convention center. And so, but this is the kind of stuff they talk about. They want to know how is the environment, how are waves, we're trying to use waves for remote sensing of the environment, whether it's crop conditions or thickness of the ice on the ocean or whatever the case might be. And so in order to extract that kind of information from the signal that's returned from the satellite, we need to understand some of that stuff. What's the mechanism responsible for the scattering? And so, but anyway, that's part of what Geoscience Remote Sensing Society is all about.
Is that why Starlink is not working at Shady Campground?
Could be. I hadn't really studied that.
So John, the loss there is the result of scattering. So,
Right.
All right. It's not, the loss is not related to absorption in the forest.
Well,
I was wondering.
so it's in a scenario like this, it's a little bit difficult to separate out the actual attenuation versus scattering, because scattering kind of has the same effect. It's removing energy from the path, right, the propagating path. Clearly some of it probably is getting absorbed, especially if there's things with moisture, with water in them, that sort of thing. But that's a little bit tough to separate out if you're in a situation like this, which part is absorption versus scattering. Together they're called extinction if you get into some of the literature. What's the extinction coefficient? How much energy is just being lost from the path or whatever reason. Right, there's all kinds of phenomena you could talk about here with respect to the scattering attenuation due to.
Well, that's a lot of loss for a short distance.
Yeah. That's, we have to look at the density of the canopy. The paper's up there. I didn't really look that carefully at the density, but it was, I think, a pretty heavily forested area.
What's the difference in between the green line and the red line?
Well, those are different models they were using.
Okay, it's just computer models.
Right, computer models. There was actually a simulation that was done, I think, on the lower curve. So, of course, one of the challenges in this kind of, when you're doing this kind of activity is the data sets you're collecting tend to be random, right? So in order to obtain a good estimate of what it is, you need to collect more than one measurement, right? You have to collect a lot of measurements to sort of do an average, right, to get a better feeling for what the canopy in general does. Okay, so at any rate, there's all kinds of things in that. And so I like this picture of our anechoic chamber we used to have. We had to get rid of it here a ways back. It's a facility like this takes up a fair amount of space. You can see, I think this took up about 1,000 square feet or something like that. And so, in addition, there's a maintenance challenge. These absorber materials, those cones you see, are the polyurethane foam with carbon powder kind of drawn into it. And initially they're painted, so they're kind of sealed, but over time the coating comes away and this carbon powder starts coming out and makes a big mess. So unless you have, the time and the resources to continually upgrade the carbon materials, it's a maintenance challenge. And so for that reason, and also they needed the space for something else, we had to get rid of this. But anyway, here we're showing a simulated, right there in the center is something we made out of plexiglass rods and so forth. It was supposed to be kind of simulating some particular plants. I don't recall what it was now any longer.
But you're not talking about, I'm a little confused by what you're, are you talking about how the antenna scatters?
No, in this particular case, I did kind of mix these up a little bit, make it a little bit confusing. My point was, I should have clarified this, had a couple different slides, but the point of the first one is when people are, one of the challenges with antennas in a general sort of fashion is sometimes we know what the current on the antenna looks like. Right, in the case of a dipole, it's well documented. It's just a sine wave looking thing. But oftentimes we don't know what it is. And so in a simulator, and so this would be more often done in some kind of electromagnetic simulator, that you're doing a sort of a thought experiment, I guess you can call that, on something that's an antenna out here. You're directing a wave at it, and you want to see how it scatters.
Okay, all right, so you're testing how something stuck in the medium is scattering out the antenna.
Yeah, but the antenna can be a scatterer. That's an important thing to think about is, when a wave, when you're receiving a wave, what happens? A current set up on the antenna. Well, current set up on the antenna re-radiates, right? So it's not just you're only collecting the energy from the wave, you're actually rebroadcasting it to some extent.
Parasitic elements.
Yeah, I guess you could call it that, but you know the usual model that we use for like a battery that's it's a voltage source and then in series with like some kind of impedance or something like that, right? But in the case of an antenna, you still include that impedance, but that impedance is just energy that's lost because it's re-radiated. So you're capturing it, part of it's re-radiated, part of it's delivered to the input and receiver.
Part of the trick is to keep that energy from being lost to re-radiation.
Well, you really can't.
Okay. You're stuck with whatever
You're stuck with it. That's just the nature of an antenna, right? You put a current on it, it radiates. When you receive a signal, it puts a current on the antenna, so it re-radiates. So anyway, that's just kind of, so that's kind of where that came in here, but I kind of mixed two things together a little bit too much on this slide. But anyway, they're interconnected. This whole business of scattering and antennas. Sometimes scattering from an antenna is important, right? If it's on an aircraft you want to make stealthy, right? Better make sure your antenna doesn't scatter, right? That sort of thing. Okay, plasma effects. So, I don't know, has DXing been very good recently, or?
We were in the middle of storms. Yeah, we were in the middle of solar storms with up to an S9 noise level.
Okay.
For the last day.
Okay.
2 days before, it was S3 to S5. But we were in the middle of a G2, G3 storm.
Okay.
Coronal mass ejections hit us on 16.
I know Sunday DX is pretty good. I got about 4 or 5 stations. One of them was all the way out into Australia on 20 meter.
What frequency was that?
14 meg.
Oh, okay. Okay, I mean, it should be pretty good in general, right? As you're close to the peak of the sunspot cycle most of the time, I guess. So, at any rate, so talking about how the ionosphere works, this is a pretty, again, a little bit of a broad brush on it, but so in this particular case, we can refer back to the, in a sense, it's based on Coulomb's law. You have two charges and there's a force exerted between them, right? And so, in this particular case, though, we're treating them in kind of a bulk way, so that the total charge within a particular, let's say, cubic meter is this small n of e. That's the charge density, how many per cubic meter. And then E, of course, is the charge per carrier. So that's the total charge. And then you're having a test charge. That's where the second E is coming from. And then you're trying to understand that force. As that force is exerted, there's also a mass involved, right? So there's a mass associated with that charge. And so if you put an electric field there, it's trying to induce the charge to move, but the charge can only move so fast because there's a mass associated with it. And so as a result, as you're applying a wave into this medium with the carrying electric field, it can only move so fast. Okay, so that's what we have something called the plasma frequency. And that's what this is talking about, how that's derived. But it's based on those particular quantities. Okay. And so from that, then you can come up with an effective impedance associated with the plasma and then interpret that in terms of reflection coefficient and so forth. But if you look at that equation at the bottom of the plot there, you can see that as omega, that's our operating frequency, right? You can see that when that's lower than the plasma frequency, what happens?
Repeat that question, John.
Okay, yeah, exactly. Okay. Omega squared is less than omega plasma frequency. You take a square root of a negative number, and you've got a J that pops up, right? And so that J is looks like a capacitor or an inductor or something like that, right? And so you know that at that particular point, less than that plasma frequency, according to this simple model, you're not going to propagate any energy through that plasma. It's a little more complex than this when you include the losses and so forth associated with this particular mechanism. But this is ignoring those losses, but this comes out pretty close. But of course, when you exceed the plasma frequency, especially when you exceed it a lot, then it just looks like free space, right?
When it's exactly the plasma frequency, you have a real problem because you get zero.
Yeah, that's right.
What's the physical phenomena of that?
Yes, when it's right at the plasma frequency, yeah, I would say it's still, it's very large at peaks at the best, right? So it's still going to be reflecting. It just may not have the phase shift anymore.
So, is this plasma radiation out of the sun?
This,
Plasma come
so the plasma comes from the charged particles from the sun that are interacting with the gases of the atmosphere. Right? And
So you're talking about the ionosphere.
I'm talking about the ionosphere primarily. And
So
so
you can actually calculate how much and what kind of reflection you're going to get based on the plasma frequency and the frequency that you're operating.
right.
Now, is there data available?
Yes.
That we can pick up that says that the plasma frequency at a certain altitude is this?
At this particular time, yeah, I mean, there's sounding going on regularly.
Yeah, ionosondes will tell you that data and tell you what the height of that reflection is.
Okay.
I'm not sure if that comes out as a plasma number, but it comes out as a frequency of the ordinary wave that's being refracted back down.
So I'm not sure exactly where the best source is for the updated material. I think QSL.net or something has some of that. Right?
There's NOAA has some data on that. The Aussies have a number of sites that are on that. Easiest is solarham.net, and it has several other links to some of the other ongoing scientific governmental
Okay.
things that are there.
Okay. Yeah, it'd be good to have the links that you described. I don't have the current stuff.
That's what it looks like
Yeah.
when you're looking at it.
Okay.
Everything. I pulled up later and show you what
Okay.
information you
I
get.
guess when you're here, you're looking at some of that stuff.
Yeah.
Okay.
Yeah.
Oh, yeah.
Dave, is that month or is that something?
MUF is based on what the FOF2 is. Maximum usable frequency is usually about 80% of the MUF. I'm not sure about, I'm trying to wrap my head about plasma. I'm not sure.
You're getting your A and K indexes and everything like that off of that. That's telling you the activity of the solar interaction.
Yeah.
So this particular plot is
Yeah, there's, okay.
this is provided by QSL.net, and roughly the maximum usable frequency is 9 times the square root of that number. That's
Yeah.
And so I
can see the F2 layer. You can get the maximum usable frequency out to the right on the bottom scale.
And I think I saw some curves. I think this one's a little on the low side. I saw some that were out closer to 10 to the 30.
Yep.
So
That's in kilometers?
this is
It's in meters.
yeah. Looks like
That's the height. That's the height of the refraction.
Give you a little better zoom in it.
miles.
yeah, so ways up.
At night, the F1 and F2 layer collapse, and you just have the one layer. But you can get from the ionoson, you can get 5-minute samplings of various locations around the world. They're shared scientific data all over the world. We are fortunate to have an ionoson in Austin, Texas, so we can get a pretty close reading as to what HF is doing in Texas.
Yeah, that's for planning purposes, right?
Yeah.
So at any rate, this kind of gives, I think this works pretty well. If you look at, I think where this particular peak occurs for F2 and this one, it's more like maximum useful frequency is closer to 10 megahertz. But if you look at some of the others where it's closer to 10 to the 13th, I think it puts it up closer to 30 megahertz. So. But anyway, it's just pretty interesting phenomena. And this plot, contrast isn't quite what I'd hoped it would be, but it kind of gives an idea of what's happening in daytime, nighttime. So you can see there are some absorption type phenomena that occur as well, like for the medium frequencies during the daytime, as the wave is propagating into D layer, it's largely absorbed. But we have a fairly strong reflection at lower frequencies, but it's pretty low down compared to the, say, F layer and so forth. Of course, the HF depends on particular value of the electron density, charge density, and then at night you can see that the medium frequencies are becoming more active, right, in terms of skip, because the D layer is gone. And so it's the E layer is then causing us to have longer range with the medium frequencies. And the lower frequencies are now skipping at a higher level too, so they're extending further out. So anyway, it's pretty interesting phenomenon, right? So. Okay. Anybody have questions or? Okay. So tropospheric refraction, I did want to say a few words about this. You know, this, when we talk about the effects of tropospheric refraction, we're usually thinking more in terms of like VHF, UHF, that sort of thing.
Yeah.
But nonetheless, you can see some interesting things happen. So refractive index is only slightly different than 1, right? 1 is refractive index of free space. And so the air and so forth is, even though we have these other things going on in the air, it doesn't change the refractive index that much. And so that's where we define variation from the small n, which is close to 1, to these cap n units, because we're talking about 10 to the minus 6 here. And so you can see that this is a pretty well accepted expression relating n units to things like temperature, degrees Kelvin, air pressure in millibars, and partial pressure water vapor in millibars. And again, because these vary over height within the troposphere, they can cause waves to either bend away or to bend toward or even duct in some cases. So, let's see, I think I have one slide that kind of shows those different things. Okay, so the ducting is more often seen around coastal areas because of how the inversion and so forth occurs around the coastal area. And so this phenomena was first observed. I'm trying to remember what it was. There was someone was looking for a ship on the radar. They noticed a ship on the radar, but nobody could figure out where it was. Well, it was actually much farther away because of the ducting.
I think the Navy lives on that mathematics. So because they have beyond the horizon sighting, they don't want to be seen. So they know where that occurs.
Oh,
So
yeah.
you can say I sight that spot.
Yeah.
Cold fronts will affect ducting as well. When you get a cold front that comes down from the Panhandle and stalls along the Gulf Coast, and you get ducting from Brownsville all the way along the Gulf to Mississippi out in the Panhandle of Florida. It's just wild.
Okay. Well, that's interesting. You know, back in the days before we had the digital TVs, I remember, you remember watching TV and every so often some station would show up from Virginia or something like that, right?
So Channel 2, I could watch Channel 2 in Los Angeles on a cold, December night. You could turn that antenna away from the Dallas-Fort Worth station and go west. You can see KNXT on Channel 2 in Los Angeles.
I had it set up in a field on these days, just strictly PBX. I just pointed toward the coast, and at some point I might see Maurice and Maureen doing exercises down in Louisiana, but with a picture of the coastal Tahoe, whatever, with a picture of the air. Just in waves, particular.
It's frequency selective, something.
It would be on like a phase, 525 lines,
Yeah, and if you're interested in trucks and everything on it, there's a site called DX Maps. You put in your main grid square, and it'll tell you, like on 6 meters, when it's opening and how far it is from your physical location where you can expect the opening to go, the distance, and the latitude and longitude you should be able to get out of it.
Okay.
It sends you alerts throughout the day.
all that in which.
DX Maps. Yeah, I'll go through that here in a little bit. But yeah, you put in your grid square, and it will blast you with information of when it's opening and where it's opening to. So there's whole sites dedicated to that. Now I just had a radio that could do 6 meters.
So at any rate, these are just different phenomena that sometimes can be observed. It's the subrefraction. Of course, waves can sometimes be bent away from line of sight too. So that's depends on. That's where I was talking about the obstacle height. If you don't leave a little margin and the wave has this kind of subrefraction, you could still reach into that first Bredow zone I was talking about. Okay, hydrometeors. Are we at a time limit here?
There's no time limit.
Okay, all right. Hydrometeors, have to throw that in there, right? I just want to be as complete as possible. So,
Meteors.
that means anything in the air that's water-based, right? Could be hail, could be fog, even, or rain, whatever. So anyway, that's just a broad term that's used. And so when we're talking about, especially raindrops, we usually use this thing called me-scattering model. And so this is a model that's been around for quite a while. It's on studying the scattering from a metal sphere. And it has some interesting behaviors. You can see how if the relative frequency, so the x-axis is circumference relative to a wavelength. So you can see if we get down to that much smaller levels, a very steep rise in the scattering. That's called Rayleigh region. Sometimes you'll hear that term. But then we get into this kind of resonance region, and then as you get farther out, it's actually equivalent to the area of a sphere, right? The area projected by a sphere. And so, anyway, when people are, there are documents on like weather radars that talk about a refractivity, a reflectivity called a Z parameter. I don't know if you've seen that or not. But anyway, they're using this as kind of a basis for determining what that Z parameter looks like. So at any rate, the Rayleigh regime is, again, that steep part of the curve, and that's where most things of interest occur when you're talking about radio frequencies in particular. So this one, if you don't mind zooming in, might be a little easier to read. Thanks. Okay, so here you can see it's projecting onto, wavelengths go from down to 100 nanometers all the way up to 10 centimeters. And so you can see where these different types of hydrometeors occur. Air molecules is probably not but then we've got aerosols, and dust, smoke, haze, cloud droplets, drizzle, and so forth. All that kind of fits within the scattering range. And so Sorry.
at the top there that just calls out the different
Oh, right, great.
frequencies just
So the microwave,
for reference.
thermal IR, and so forth. Yeah. So we know that as we get up into what, well above 10 gigahertz or so, that that you can have substantial fading, right? If you still watch satellite TV, for example, you see some fadings, fade out so briefly, oftentimes. But at any rate, the weather radars that we normally see on TV, they operate either at 2 to 3 gigahertz. That's the S-band radar. People talk about S-band. Those are more useful because it's low enough frequency you can penetrate out quite a ways to pick up phenomena 100 miles away or whatever. But more sensitivity if you move to like 5 gigahertz, that's called C-band or X-band in some cases, or if you want finer scale, which is 10 gigahertz. But you can't penetrate through as far, right?
Just a question.
Yeah.
Sorry. Didn't we have like Jim, talk about microwave? Like one of the things they did was they would use thunderstorms and they would do gigahertz bouncing off of thunderstorms to make contact. I think this is just understanding that this is kind of the principle.
Yeah. This, you could use it as a way to gain a skip, or if you're trying to obtain information about the storm itself, in terms of the rotation and density of rainfall, wind speeds, all that sort of thing. You can make use of this type of phenomenon. Kind of stuck here.
I have to release it.
There, got to get you
Okay, thanks.
back in.
All right. And so, at any rate, you can spend a lot more time on this particular phenomenon. In fact, I found an ITU document that talks about weather radars, different types. If any of you's interested, I can send you the link to it. But anyway, this just gives you an idea of the attenuation that occurs through these are different rainfall rates in terms of millimeters per hour, all the way down to 10 gigahertz. And you can kind of extrapolate somewhat linearly and get a pretty good idea below that what it might look like. And this is my last slide. I wasn't complete without talking about the effect of gases on the spectrum as well. And so, fortunately, we have, so this is kind of gives you a picture of the atmosphere in a very broad sense in terms of the opacity, how transparent is the atmosphere for transmitting different wavelengths. And so you can see over this region where we see like 1 terahertz up to 10 terahertz, that the atmosphere is largely opaque. Things don't propagate very well. There's just too much molecular activity. And then, of course, as you move to the right side of that, moving more toward the visible, fortunately, we have kind of a blank spot on things we need to see, right, for the light spectrum. But you can see once you get much below that, down into the infrared, you're starting to see all these other effects, right, CO2 and H2O and so on.
Thankfully, we have that.
Yeah, that's right.
For the infrared.
Thankfully, we have that, right? And so most of this, if you look at the spectrum associated with different molecules, it'll have spectrum associated with rotation, with stretching, with bending. Those are mostly somewhat lower frequencies, but then of course you have transitions of the electron within the molecule, right? Those are much higher frequencies, and so on. But you can see it extends down into frequencies that are now more commonly being used. So we go up close to 100 gigahertz down into the 70 gigahertz. What kind of applications do we have there nowadays? So we have like automotive radars, right, operate in the 70s gigahertz kind of range. Yeah. And so, and 5G is kind of encroaching, and there's already on the horizon the 6G, where they're going to use frequencies up close to 100 gigahertz. a lot of things going on.
Okay, so dumb question. What is a stretching resonance?
So, like H2O, so stretching would be associated with the two, what hydrogen molecules connected to the oxygen, maybe like stretching away from the oxygen molecule. That would be an example of stretching.
And stretching, what does resonance have to do with that?
Well, those are all types of resonance.
If you're at the frequency where it's interacting with it,
Right.
The absorption is a characteristic of it interacting with that media,
Right.
and that media then determines the attenuation, i.e., water
Right.
and water vapors. If you're at the frequencies right here, you get different attenuations based on it, and it's the interaction of the electrons.
Yeah, the electrons are within the molecule itself. Yeah, those are that you can actually.
You're imparting the energy.
Yeah.
It's absorbing the energy, or it's imparting the energy into that. And there's where you're getting your loss.
Right.
Is it a zone where you have water is a gas and water is a solid and they're sort of going back and forth? Come the gas now it's solid.
Well, in this particular case, it's more of gas. Yeah, it's more of a gas in this particular. But as the pressure, if you go up to higher elevations where there's low pressure, you tend to see much more distinct resonance features, much sharper lines. As you go farther down, because of the interaction of the molecules with each other, you see a broadening in those kind of spectral effects. Yeah, they're true mechanical resonances, just like any other mechanical
So it's
resonance.
basically the frequency at which that molecule becomes resonant, depending on how it's stretched or compressed.
Yeah, it causes it to stretch if it's lined up right, or to rotate. Like in a water molecule, it's polar, right? So you can rotate it with the right.
Pretty different depending on the person's water, the state that it's in, be it vapor, liquid, or solid.
Uh-huh. Right. So,
It would resonate differently in different states.
right,
Yeah.
Different brain.
right.
That's the reason why they can, on radar, see, well, that looks like hail, and not just rain.
Right. When you put water into like a liquid form, its effect is much broader than just spectral lines, because now it's a bulk quantity where they're in a very compressed sort of interacting. And so if you look at, for example, the dielectric constant water, you'll see it does somewhat peak in terms of like at 2.4 gigahertz or in that ballpark, right? That's where we operate microwaves, right? But you'll see it's pretty lossy throughout the spectrum until you get down to these very low frequencies. So it's not these distinct spectral features once you get into those liquid and solid form.
You don't mind, right? I'm trying not to dominate this, but you showed something that's really got me puzzled. Back to ground waves. And I know on the earth, in the early days of, if you will, Marconi radios, a lot of ships at sea were using that. I understand that ground waves propagate really especially well over salt water. And yet, when I look at the photographs of all those old ships and stuff, those antennas were all horizontally polarized.
Well, that's the only way they get out.
Well, that's what I was thinking. So why did it work so well?
It didn't.
If the ground wave works vertically polarized versus a horizontal.
Yeah, so I mean, we'd have to compare the two, right, to see.
Pretty
whether-
much, if you're made anyway, it's not all.
If you have change the horizontal, then you make it curve. You have supporting wire, the radiating ones are hanging on.
But okay, and that would make sense because you got a capacitive. You got a capacitive cap there, but and that may be the answer to the question.
I think they didn't know any better.
Well, they are really good. Yeah, they're hitting trouble. Yeah.
Really well.
Well, it has to be used, right? Well,
But are you,
just like they were talking about on Marconi when he did his first radio antenna and everything, they were talking about it would have been more efficient if you could just put up an 80-meter dipole.
well, wait a minute, you're using spark.
Yes.
So
He was flattering.
Yeah.
He was flattering.
you're splattering off a lot of spectrum getting used.
Maybe it was reflecting on.
Yeah.
Well, I didn't think you talking hired 300 coyotes anyway.
Yeah, it was all wasted. That's why I gave it to the ham.
That's right.
Everything above that.
About 200 meters was, give it to the ham. They don't know what to, they'll figure out something there.
Okay, let's
Very
extend
good.
what I have.
Thank you, John.
Yeah.